Hi, so welcome back to this lecture where we will work out the solutions of the problems given in assignment 2. This was for ordinary differential equations. And this was the first problem. There were 5 of them, so we'll work out each of them one by one. The first one was the differential equation, second order linear differential equation with a sinusoidal input. We have done this one before as well by the method of undetermined coefficients. So we know the general solution of this really. But the question is to show that the particular solution of this differential equation can be written like this. Okay, this is an operation 1 over BD plus C minus A square. This is, as usual, the element of the ring of formal power series. Okay, this is acting on this. Okay, this function. So you just have to show that this differential equation, the particular solution of this differential equation can be written like this, where d, of course, is the usual d dt or the derivative operator. Okay. Now, we already know the particular solution of this differential equation by our method of undetermined coefficients. Okay. What was that? It really was. So let me just write it down because we already have the answer from another method, that is the method of undetermined coefficients. Let me just write it down for our reference, but we will of course solve this one. So that was 1 over C minus A square plus A square capital B square, and then you had C minus A square with sine AT plus B, and then a negative small a capital B cosine AT plus B. Okay, this was the particular solution by our methods of undetermined coefficients. We already know it. But of course, we have to show that the particular solution can be written like this, but we don't know yet that this is the particular solution. We just have to show that. So let me just rub that out and look at this differential equation look at this expression by itself. Okay, what does this remind us? It actually reminds us of a first order linear ordinary differential equation, and that equation will be BD plus C minus A square, this whole thing acting on, let me write a different variable, y, I'm not using x, equals A sine AT plus B. Okay, why is this? Because you see, if somebody asks you, by the way, I hope what is this differential equation? If you multiply this with the y, really d is the derivative operator and b is the constant. So you really have capital B dy dt plus this on y is c minus a square times y. That's just multiplication by capital A sine AT plus b. Okay. That's the first order linear differential equation. If you want, I can get rid of this b here, divide by that b all the way through. So really what you have is dy dt plus some constant times y, and then an input function on the right. That's a function of the independent variable. So this really is a linear differential equation. And if you want, you can write it in a much simpler form. Don't write these complicated constants. It's just, if you want to call this whole thing alpha, this is just alpha y equals, let's say, beta sine AT plus B. Okay, where beta is capital A by B. Okay, don't confuse beta with B. We'll write beta with a long tail here. Okay, so this really is a first order linear differential equation. Okay, and this is this. Okay. Now, if somebody asked you to find the particular solution of this differential equation, this would be it. Okay. See, because this is the operator on the y, acting on the y variable here. So if you operate on both sides by the inverse of this, from the left hand side, you would just get y, which would be the particular solution. And from the right hand side, the inverse of this, which is this, will be acting on the function, or the input function. And so this really would be the particular solution of this differential equation, which is this differential equation. And we know how to solve this differential equation. We know the particular solution of this differential equation because it's linear and it's first order. We've done it many times before. It's going to be e to this alpha will come here, minus alpha t. There's going to be an integration e to the alpha t. Then there's going to be this function here, beta. I'm going to write beta outside because that's a constant. So here's what you have. You're going to have sine AT plus B dt. That's all. Okay. Well, the general solution will have some constant times e to the power minus alpha t here, but we're not concerned with that. We are concerned with the particular solution, and this is what it is. And we know the answer if we can solve this integration. It's a very standard integration that we have all done in school. It's solved by parts. You would really have to use by parts twice here. Okay. And that was a trick to solve this integration. I'm just going to write it here. I'm sure all of you will be able to do this. I'm not going to teach integration here. But this is a very standard form. I'm sure even if you haven't done it, if you do it once, you'll be able to figure this out. This answer is really it's going to be 1 over this A and this alpha will come down here, in this form. So you have A square, that's going to be A square plus alpha square, the distance really the square of the distance between A and alpha, or, right angle triangle. And then this one is going to have alpha sine AT plus B minus A cosine AT plus B. That's the solution of the integration. That's the integration. Okay, that's the integration. So if I just write down what this, let's just do it here. So yp therefore will be, yp here will be, if I just write down the constants, so beta is just A over B. Okay, then, there will be I forgot, there will be e to the power alpha t here, because the e to the power alpha t comes through from the integration. Okay, so this is going to be e to the power alpha t. Now you have beta, the e to the power minus alpha t will multiply this instead of this. I'm just going to copy this. E to the power minus alpha t will cancel with e to the power alpha t. So you're just going to get 1 over there, and then you're just going to be left with this term. It's going to be 1 over a square plus, well, what was alpha? Alpha was this thing, c minus a. So it was just c minus a square. It's alpha square, so I have to put a square, and then there was a b below in alpha. So b square, okay? And here you have alpha, which is again c minus a square by b sine at plus b minus a cosine at plus b. Okay, so this becomes this if you put in the right constants, and if you see this, this is just going to give you what we had already found. Okay, so this will just give you, this b square will come here. I hope you can see that. Okay, this b square will come here, and this one, so the b square will come on top here, will cancel with 1b, so there will be 1b in there. The 1b, if you multiply it through, this b will cancel with that, so you will get this term, and that 1b will come in here, which will give you this term. Okay, and here you're left with this term, c minus a square whole square plus a square b square, and you have that capital A. Oh, I forgot that capital A here. I need a new pen. So I forgot that there was a capital A over there. Okay, this A would come through. All right. So really, what we see is that yp, which we said is the yp. Therefore, from one angle, yp is this thing here, this expression is the particular solution of this differential equation, okay? This is the particular solution of this differential equation. And we have found the particular solution, okay? We have found the particular solution by our known methods of solving a first order linear differential equation. And it matches with this, which was already what we knew was the particular solution of this differential equation. This is this. So therefore, xp is yp is this. And that's what we had to show. We had to show that xp is this. Okay, I hope it's clear. It's a roundabout way of doing it. Okay, let me just go over this cycle once more. I looked at this expression, thought that this was the particular solution of this differential equation. Okay, but I know how to solve this differential equation. So I've done it. This is a particular solution of this differential equation. So this must be this. That is, this must be this, because this is this. Now this we already know from our methods of undetermined coefficients was the particular solution of this. So therefore xp must be this. Okay, I hope that's clear. Okay, so this really is how you solve or show that this is what it is. Okay, now there was another part to this problem. The next part was to just show, I'm going to rub this out. I'm going to leave this one here. So the next part was to just then show that the answer, if you find out the answer from here, you would just get this, okay? In other words, it would match with what we had already found before by our methods of undetermined coefficients. If you now solve this one, you should get this. Well, one way of doing it is like this, because I know how to solve this and we got this, okay? Another way, because we looked at this like the particular solution of a first order differential equation, and if you solved it, you would get this, and we've already done it. But there's another way of doing it. So what happened really was something really amazing, because the way we found if this is the differential equation with the sinusoidal input, the way we can find the particular solution is so the particular solution originally of this differential equation could be written as 1 over d square plus bd plus c acting on sine at plus b. This would be the original way that you would write the particular solution of this differential equation. And we have shown that this is this. This would be the particular solution of this differential equation. But we've shown that this is actually this. So in other words, what's common between this? It's just that the BD term is there, the C term is there, except that D square has been replaced by minus A square. Okay. So if you're going to find the particular solution of this differential equation, all you have to do is to just replace the D square term by minus A square, and you are one step forward, you're one step, ahead, or you go one step further to finding the actual particular solution. This you still had to solve this because there is a D. This is still an operator. But from here, this way of expressing the particular solution tells us that one step forward from here on would be to just replace the D square term by minus A square, and you're there, okay, almost there. You just need to now solve this. So let's just do it. Let's just use the same trick. 1 over, so xp is bd plus c minus a square sine at plus b. This is what we have just shown. Now, how do you solve it further? I want to use the same trick that I have found. That is, if I had a square, if I had a d square here, I could just replace it by minus a square. I want to use the same trick. The way you can do this is to multiply both up and down by, let's just write this here. You can multiply both up and down by this itself. So, except that you have to put a minus sign in here. C minus a square BD minus C minus A square. Well, what if you do this? Now, remember, we are working in a ring here, okay? And this is the multiplicative inverse of this, and we are allowed to do all of this because we know the inverses exist, the multiplicative inverses exist. And that's just the algebra part of it. We don't have to worry about it. We have established that part, so we are free to do all of this. And if you look at it, this will just give you what? It'll just give you, of course, it gives you BD minus C minus A square on top, but then this one gives you a B square D square, okay, and a negative C minus A square whole square. Do you see this? This is just to explain all A plus B into A minus B formula, okay, A plus B, A minus B, and this is acting on capital A sine AT plus B. Okay, of course, now we have the same form as before. We got a D square down here as an operator acting on this, and so I can use my previous trick to just replace this D square by minus A square. So what I will have is a BD minus C minus A square, and I will just have a negative A square B square minus C minus A square whole square. I can just make the whole thing positive, all the negative terms, by making this one plus, this one minus, and this will go, okay? And this one is just capital A sine small a t plus b. So I'm done with the denominator part, so I got this. All you have to do is to just multiply this now, okay? Well, if you multiply this, you see what you get is this, okay? Because first of all, this is constant. I don't have to worry about it. This is just a square capital B square. Anyway, I don't have to write this. You can see it from here itself. This is just this denominator. If you multiply this through, you will get C minus A square with this term as you have here. The A is a capital A, that is a constant, and this minus BD will act on it to give you a minus capital B. The D will make it a cosine AT plus B, but that small a will come out because you're differentiating it, so you will have a minus AB term here, okay? So really, there's no need to write this. This is exactly what this is, okay? So therefore, the way, first, the purpose of this problem was to just give you a process of how to solve a differential equation with a second order linear differential equation with a sinusoidal input like this, okay? It's just that first you replace the d square by the minus a square, and then what's left of it can be adjusted by this ring operation here to bring in the same trick of putting a minus d square again in the denominator, replace that by minus a square again, and whatever left on in the numerator is just differentiation, and you differentiate that out, the function out, and you will get your answer. So that was the purpose of the problem, to give you the whole picture of how to solve a differential equation using the D operator method, okay, with a sinusoidal input. Okay, that's the important thing here. Okay, that was the first problem. The second problem was just an exercise in this. The second problem was this. Problem 2 was just an exercise, is to show that find the general solution of x double prime, this double differentiation, minus 2x prime plus x equals 2 sine t plus 3 cosine t. Well, it's just an exercise just all you have to do is to implement what we learned in the first example. This really is another way of writing this, is just d square minus 2d plus 1, okay? That's x with 2 sine t plus 3 cosine t, okay? what do I do? The way I can find the particular solution is to act on the right hand side by the inverse of this. So I'm going to get a 2 over this d square minus 2d plus 1 acting on the sine t, and I would also get the second one, which is the 3 times d square minus 2d plus 1 acting on cosine t. Now, the important thing to realize here is the reason I've put this cosine term here as well is because the cosine acts exactly the same way as sine, and that's really something that you have to figure out while doing this problem. There was no, if you go back to the first problem again, there's nothing different about sine and cosine. They act exactly the same way because that integration works out like that. That integration by parts which you had to do, that worked out the same way for sine and cosine. Okay, so sine and cosine will behave exactly the same way. So because you could replace d square by a minus a square, that you could do the same with cosine. If you know, okay, so let's just do that. So that would be if I replace the d square by the minus a here is 1, so minus 1 square is minus 1. Okay, so you have to be clear. This minus 1 square is minus 1 because this minus 1 square means minus of 1 square, which is minus 1. It's not the same as minus 1 whole square, which is 1. Okay, so when I say minus of 1 square, I should say that. Okay, so minus of 1 square is minus 1, which will cancel with this plus 1, and you are left with this minus 2 and this 2 will cancel, so you're left with minus 1 over d sine t. Plus, the same thing will happen here. 3 over this minus 1 will cancel with this 1. You're left with a minus 3 by 2 d cosine t. Well, you could do the same thing, just multiply up and down by d, okay? And then you would have minus d, a d square, sine t, and then a minus 3 by 2 times d and a d square cosine t. Again, you can replace the d square by the minus of 1 square. So that will give you the minus, which will remove this minus. So you just have a d on sine t, which is really cosine t. I can just write that out straight away. And similarly, the minus of 1 square will remove this minus. Okay, and you're left with 3 by 2. But d on cosine will give you sine, but with a minus sign. So that's the answer. It's just plain and simple once you learn the trick from the first problem. Okay, let's go over to the third problem. The third problem says that, well, this is the problem. The third problem says that x double prime plus bx prime plus cx, that's the differential equation, second order linear differential equation, with the product input like this, tv. Okay, t and a v is a function of t. Okay, show that the particular solution can be written like this. It's a rather untidy one, but it won't be that untidy once we work that out. 2d plus b over d square plus bd plus c, this whole thing on 1 over d square plus bd plus c acting on v. Okay, this is what you have to show. Well, we have already done this with the method of undetermined coefficients. The particular solution for this was given by t times u1 plus u2, okay, where u1 and u2 were functions of t, and they were given by, u1 was given by this differential equation. You have to go back and check, go through the lecture where we had actually solved this differential equation. Okay, we've done the entire problem to solve the particular solution of this problem, particular solution of this equation by this method of undetermined coefficients, u1 and u2. u1 was given, I'm just reviewing it, I'm just recapping it. So u1 was given by this differential equation, u1 double prime plus the same differential equation, except with, instead of x, you will have u1. So u1 prime plus c u1. This was that with a v on the right hand side. u1 was recovered from this differential equation, and u2 was recovered from, well, same left hand side, cu2, but with minus 2u1 prime minus bu1. Okay, this was what it was. So, and if you find u1 from here, u2 from here, just put them in, you would have your particular solution. You have to show that this will get the same form. Let's see. So this one, how do I find u1 from here? Well, the particular solution of this is going to be, I'm not writing p here because we know we are finding particular solutions. So the particular solution of u1 for this one will be, well, 1 over d square plus bd plus c, because that's the operator acting on u1 here. Okay, that's u1 for you. What's u2? u2, let's do it here. u2 is, well, the same inverse operator acting on this. So u2 is d square plus bd plus c acting on this right hand side, which is negative 2 u1 prime plus b, bu1. Well, what's this? This is, or let me just write it once more. I want to keep this just for reference. This is, I can take the negative sign out, that's a constant. This is 2d plus b acting on u1, isn't it? You see, the 2d, this is a derivative operator on u1 will give you u1 prime, and the b with u1 will just give you bu1. So u2 is really this. And what was u1? u1 was this. So let me just put that once more here. u1 is d square plus bd plus c on v. So that's u1 and that's u2. So let's just put all of them together in xp. So xp gets t times u1, which is t times, so t on d square plus bd plus c plus u2, but u2 has a minus, so minus 2d plus b with d square plus bd plus c whole square. I'm writing this as whole square. Remember, these are all happening in a ring, okay? And this one acts on u1 acts on v. This thing acts on v. u2, which is this, also, the operator also acts on v. So, this is just a simplification of this, okay? So just you can take this one out, 1 over d square plus bd plus c, and v, you can take that out. And inside the bracket, you're left with t minus 2d plus b over 1 of the d square plus bd plus c. And on the outside, of course, you have this term, okay? So really, by the method of undetermined coefficients itself, we had solved it. It's just that we have to put this in the d operator form, and this would be the formula. That's all there is, okay? All right, that's the third problem. Let's do the fourth problem. The fourth problem is just an extension of this. It's just that if you had t to the power n here instead of just t, let me just write that once more. If you had t to the power n here, the particular solution of this would be just what you had exactly, but to the power n here. That's the problem. That's what it says. This is number 4. Number 4 says you can do this. If you had a product term on the right like this, then this would be the answer. Let's just do it. And I said that we can do it. In the assignment, it was asked to do this by the method of induction, which really means, and I've explained it in the problem itself, what is induction, mathematical induction. Let's just go over it for 1 minute. Mathematical induction here means that if you have a mathematical statement, if you have what I can call a proposition, some statement, okay, which is true for all, or which can be checked for all natural numbers. In other words, let's say I'm looking at this thing. We know that some constants a plus b to the power n. I'm just giving an example. This formula is the binomial formula. We all know this. This is summation r from 0 to n. N choose r, a to the r, b to the n minus r, or a to the n, whatever, okay? You can. Now, this is a binomial theorem, okay? The formula by binomial theorem for a plus b to the n. And it doesn't matter what n you put 7, you put 17, you put 17,000, whatever you put, this is the formula. So this statement that this is equal to this is true for all n, okay? It's a statement which is true for all natural numbers n. So the way to do this is, the way you prove this by the method of mathematical induction is that you write, let's say my statement Pn is this, is that Pn is this statement, okay? You call this thing Pn, okay? This is the proposition, the statement for a particular n. Now, the way you do this first is to show that P1 is true. In other words, put n equals 1 and you show that it is true. It is always true. If you put n equals 1, a plus b will be a plus b. And, there will be only 2 terms, 0 to 1. R will vary from 0 to 1. 0 will give you the a term. 1 will give you the b term. That's all. The first statement is always true. The second statement is, the second step would be, if you assume that P1, P2, up to Pn, these are all true. In other words, up to some chosen natural number, if you know that this statement works, in other words, this expression is this formula, if you expand it, if you know that these are all true up to a number n, then using this, if you can prove that Pn plus 1 is also true, in other words, the statement for the next natural number is also true, using the fact that the previous ones were true, if you can prove that, then you have shown by mathematical induction that this statement is true for all n. Okay. In other words, once Pn plus 1 becomes true, then by the same method that you have used, you can then prove Pn plus 2 to be true, and you can go on and on. So this becomes true for all n. So you can try this as an exercise to show that this statement is true. You can try it by mathematical induction. So let's just do this. Okay, I want to show this by mathematical induction. So my statement is, this is going to be my statement. Pn means that the particular solution of this differential equation with this input, okay, with the t to the n here, the particular solution of this differential equation is this. That's my statement for n. Okay, if I vary my n, the statement would vary as it, if there is t cube, I would say that the particular solution will be this cube times this. Okay. Oh, there was this v here. Okay. Anyway, so this is the nth statement for a natural number n. I want to show that P1 is true. I'm going to follow the steps here. First, I'll show that P1 is true. Well, P1 was true by question 3. When n was 1, we had shown that there was 1 there. Okay. The particular solution was with 1 over here as the index. And we have shown that by problem 3. So P1 is true. What about the second statement? Suppose I assume that P1, P2, up to Pn, they're all true. I have to show that Pn plus 1 is true. This is the task. This is what I have to show. Let's just show. If I can show this using my assumption, then I have proved this for all n by the method of mathematical induction. Let's just do that. So I'm going to look at this differential equation now with n plus 1, and I'm going to show that the particular solution of this is going to be this. That's my task. Okay? Of course, this was the statement. But now my task is to show this. If I show this, then I know that this is true. Okay. So xp would be, so let me just write this differential equation again. How can I write? I can write the right hand side as TNV, isn't it? And let me call this by a new name. Let me call this V1. Okay? So really what I have here is, so let me just rub this out. So what I have here is, I'm writing this as TV1, where V1 is just T to the NV. Is that fine? I've just broken this up. Okay? Right. But we know how to solve this with a V1. So xp for this differential equation, now forget this. I'm looking at this. This was just t minus 2d plus b over d square plus bd plus c, d square plus bd plus c on V1, because this is, I'm looking at the right hand side like this. So on V1. Right? Is that fine? But what is V1? V1 is this. Let's just write that out. It's TNV. Okay, so in other words, this is acting on this. I hope that's clear. Those are two brackets in there, okay? So I just want to separate this one with this one, okay? This is, you can think of this one first acting on this. But that's the particular solution of which differential equation? That's the particular solution of this differential equation, d square plus bd plus c, let me say y, something else, equals t to the nv. That's the particular solution. This is the particular solution of this differential equation, isn't it? But this is known because I have assumed that up to Pn, this is with n here. This is true. I know that Pn is true. If Pn is true, the particular solution of this should be with n. T minus 2d plus b over d square plus bd plus c nv. I hope that's clear. I'm looking at this. This is the particular solution of this differential equation, and I know that the particular solution of this differential equation is this because I have assumed that for n this is true, Pn is true. And so if I replace, so this is yp. This is the particular solution of this, which is yp. Okay? So if I replace this by this, is that clear? This is yp. This is the particular solution of this, which is written as yp here. So if I replace this whole thing by this, all I have is this. So I'm just going to get t minus 2d plus b over d square plus bd plus c. I will just have this to the power n, which is the same as this expression, absolutely the same. This is to the power n, which would then multiply to give you n plus 1, and then the v outside. So really, using this assumption, I've used only one, I didn't need all of this, but this assumption gave me a way to find the particular solution of this differential equation as exactly this. So Pn plus 1 is true. This is true from this assumption. So assuming that the statement was true up to n, I have shown that the next statement is also true. And you can go on forever. You can now show that the next statement is also true. So this is a proof by mathematical induction. This is true. Okay? All right. That's your fourth problem. Let's just do the last one. The fifth problem. Which really was, I think, just an exercise to implement this fourth point. The last problem is to find this x double prime plus 2x equals t square sine t. Just solve this problem. Well, this is just d square plus 2 on x, written in the operator form, t square sine t. And that's the, that's the t to the n v form, with n being 2 and v being sine t. Okay? And we've just found out what's the particular solution. The particular solution is going to be t minus, 2d okay, plus b. B is 0 here. Okay? This is c, remember, x double prime plus b x prime plus cx. So b is 0 by this expression d square plus 2. N is 2. I'm just going to have d square plus 2 again acting on the v, which is sine t. Well, what does this give you? Remember, d square can be replaced by the negative of a square here. A negative of, so that's 1. So negative of 1 square is minus 1 plus 2 is just 1. So this becomes 1. So this just becomes t minus 2d by d square plus 2 square t. This keeps sign as it is. Okay? It doesn't change sign at all. It keeps sine t at sine t. This operation is good. It just, it doesn't change sine t at all. So let's just do this. This is, again, we're working in a ring, so we can just multiply things. So it's just going to be t square minus 4d on over d square plus 2, and then a plus 4d square by d square plus 2 whole square, and this whole thing on sine t. Well, let's just, make them act one by one. T square on sine t is just multiplication. Minus, this thing acts on this. But let's just make 1 over d square plus 2 act on sine t. That keeps sine t as it is. So this on sine t will keep sine t. Now d on sine t will change to cosine. So you have a minus 4 cosine t. What about this? Well, d square minus plus 2 will act on sine t. 1 over d square plus 2 will act on sine t twice. But it doesn't change sine t. So the whole action will keep sine t as it is. Then d square will act on sine t twice to give you a negative sine t. So you will have a minus 4 sine t. That's your answer for a particular solution. Okay. The general solution is just, what you have to find, the complementary function. We've done that a million times before. I'm sure all of you can do this. But really, the problem was to, it's just an exercise in of the fourth problem. Implement the fourth problem. And this is how it is done. Okay. All right. So those were the solutions. I hope these will come in handy. Also, you will learn new things from solving these problems and going over the solutions. So we'll take things forward in the next lecture. Thank you.